in less than 3 seconds. An aircraft carrier launches nearly 80,000 pounds of aircraft into the sky, 0 to 160 miles per hour, in just 300 feet. That requires the energy equivalent of dozens of explosive charges every second. That is violent physics. The impossible runway. A modern fighter normally needs more than 1,000 feet of runway. But an aircraft carrier gives it only about 300 feet. Without mechanical help, the aircraft would simply run out of deck and fall into the ocean. So carriers rely on one of the most powerful launch machines ever built. Chapter 1. Steam Catapult. Steam-driven launch system. For many decades, aircraft carriers solved the challenge of launching heavy fighter jets from a relatively short runway by using a powerful system known as the steam catapult. This technology became a key part of carrier operations, allowing large and fully loaded aircraft to take off safely from the limited space available on a carrier deck. The system works by using high-pressure steam generated by the ship's reactors or boilers. This steam is directed into a long cylinder located beneath the flight deck. Inside this cylinder is a piston that moves rapidly when the steam pressure builds up. As the piston accelerates forward through the cylinder, it is connected to a launch shuttle that runs along a track on the deck above. The aircraft's nose gear is attached to this shuttle before takeoff. When the system is activated, the shuttle surges forward at incredible speed, dragging the jet with it and launching the aircraft into the air within just a few seconds. In just seconds, the aircraft reaches takeoff velocity. Chapter 2. The problem with steam. But steam solves the problem by hitting the aircraft like a sledgehammer. Sudden surge in launch force. Although steam catapults worked for decades and helped aircraft carriers launch thousands of aircraft, the system had several serious limitations. One of the biggest issues is how steam pressure builds inside the catapult system. Instead of delivering a perfectly smooth push, the pressure can build unevenly, creating a sudden and violent spike of force at the moment of launch. When the catapult fires, the aircraft does not always experience a steady acceleration. Instead, it can feel a harsh jolt before being pulled forward at extreme speed. This sudden force puts significant stress on critical aircraft components, especially the launch bar, the nose landing gear, and even the aircraft's airframe. Over time, these repeated shocks can cause fatigue and increase maintenance requirements for both the aircraft and the carrier. Another major drawback is the complexity of the steam system itself. Steam catapults require massive plumbing networks running throughout the ship, along with large amounts of fresh water to generate the steam needed for launches. So while steam catapults certainly work, they come with major downsides. The system is violent, inefficient in energy use, and difficult to control with precise adjustments during each launch. Engineers needed something smoother. Chapter 3. EMALS. Electromagnetic Aircraft Launch System. Modern carriers replace steam with electromagnetism. A motor stretched into a straight line. To solve the limitations of steam catapults, engineers developed a completely different launch system known as EMALS, the Electromagnetic Aircraft Launch System. Instead of relying on steam pressure and mechanical pistons, EMALS uses advanced electromagnetic technology to launch aircraft from the carrier deck. At the heart of EMALS is a linear induction motor. This system works through a long series of electromagnetic coils installed beneath the flight deck. When electricity flows through these coils, they generate a moving magnetic field that travels down the launch track. This moving magnetic field interacts with the launch shuttle that is connected to the aircraft's nose gear. As the magnetic field moves forward, it pulls the shuttle along the track, accelerating the aircraft smoothly down the deck. Unlike steam catapults, EMALS does not produce a sudden spike of force. Instead, the aircraft experiences a controlled and steadily increasing push. The acceleration is carefully managed by computer systems, allowing the launch force to match the exact weight and requirements of each aircraft. If steam catapults hit like a sledgehammer, EMALS feels more like a perfectly timed wave, smoothly building speed until the aircraft lifts off the carrier and climbs into the sky. But the real engineering is hidden deeper inside the ship. Chapter 4. Where the energy comes from. Power stored and released in bursts. Launching a fighter jet from an aircraft carrier requires an enormous amount of energy. A fully loaded fighter can weigh around 30 tons, and it must accelerate from a complete stop to full flight speed in only a few seconds. Achieving this kind of acceleration demands a powerful and carefully managed energy system. However, the ship's nuclear reactors do not send power directly into the catapult at the exact moment of launch. Instead, the carrier first stores large amounts of electrical energy in specialized energy storage systems. These systems collect and hold power over time, preparing it for the launch. When the aircraft is ready, the stored energy is released in a rapid but carefully controlled burst. This energy flows into the electromagnetic launch system, creating the magnetic forces that accelerate the aircraft down the deck. Because the energy release is controlled electronically, EMALS behaves almost like a digital system. The launch is not only powerful, it can also be precisely programmed and adjusted for different aircraft. Huge energy delivered in a short distance. And that precision changes what carriers can launch. Chapter 5. Future Aircraft. Aircraft carriers of the future will launch far more than just traditional fighter jets. As naval aviation evolves, carriers will also deploy autonomous drones, advanced sensor aircraft, surveillance platforms, and even heavier next-generation systems designed for long-range missions. These new aircraft types come in many different sizes and weights, which means the launch system must be far more adaptable than older technology allowed. Traditional steam catapults were designed mainly for launching manned fighter aircraft. They deliver a powerful push, but the force is not easily adjusted for different aircraft types. This limits flexibility and can place unnecessary stress on lighter or more delicate systems. EMALS changes that completely. The result is a smoother launch, less mechanical stress, and far greater flexibility for the wide range of aircraft that future carriers will operate. And more aircraft types from the same deck. This is not just an engineering upgrade. It is a systems upgrade. Carrier relevance now depends on launching more aircraft types, more efficiently, with less mechanical punishment. And the aircraft that matter most may not stay above the ocean at all. As the surface becomes easier to monitor, the real competition is moving deeper. In the next briefing, we examine the thermocline loophole and the autonomous systems hiding beneath it. Watch that analysis now. Dismissed.